We shall continue our discussion on molecular vibrations, where the molecules are all made up of atoms, and these atoms are linked by bonds. So each bond in a molecule resembles two balls connected by a spring, where this spring or the bond can undergo stretching vibration as well as compression. That means it has an equilibrium bond length. An equilibrium bond length is always maintained for this stretching motion and compression. And this characteristic vibration of a particular bond is called its fundamental vibrational frequency or natural vibration. As you can see here, as we are considering bonds as springs, Hooke's law for an enharmonic oscillator is applicable to a bond. So here we consider a bond made up of two atoms having mass m1 and mass m2, so that the reduced mass of the bond that is defined as mu is equal to m1 into m2 divided by m1 plus m2, where m1 and m2 are the atomic masses of the two atoms bonded together. So here you have an equilibrium bond length where the nu is equal to 0 represents the fundamental vibrational frequency. And it is surprising to note that even at nu is equal to 0 or ground vibrational energy level, the molecule's energy is not 0. The vibrational energy is not 0. That means even at nu is equal to 0, the molecule is having a vibrational frequency which is called the fundamental vibrational frequency or natural vibration. And when it absorbs a photon in IR region, it undergoes transition from its nu 0 level to the first excited vibrational level. And similarly, it can absorb photons from IR and undergo transitions to different excited vibrational energy levels until it absorbs a radiation which is equal to the ionization energy where this bond breaks. So until the molecule absorbs an energy equivalent to the ionization energy, it will be vibrating faster. That means with a higher frequency, absorbing each photon, undergoing transitions between the different vibrational energy levels. So according to Hooke's law is applicable to spring motion. So as we are considering bonds as springs, Hooke's law is applicable to bonds also, where nu is equal to 1 by 2 pi c into root k by mu. And we know that nu bar wave number is equal to nu by c. So here we are expressing frequency in IR as wave number, as we have already discussed in the previous video. So this nu bar in wave number in centimeter inverse, that is equal to 1 by 2 pi c into root k by mu. Here k is the force constant of the bond, which depends on the strength of the bond. That means for a single bond, the force constant will be nearly equal to 5 into 10 raised to 5. And for double bond, it is 10 into 10 raised to 5. And for a triple bond, it is 15 into 10 raised to 5. That means as the bond strength increases, the force constant also increases. And mu is the reduced mass, where it is equal to m1 m2 by m1 plus m2, and c is the speed of light. In meter per second, it is 3 into 10 raised to 8 meter per second. But normally in our problems, we are dealing with the frequency or wave number in centimeter inverse. So we are using the value 3 into 10 raised to 10 centimeter per second. So what is the significance of Hooke's law? It states that the vibrational frequency of a bond is directly proportional to the force constant. That means the strength of the bond. So a strong bond can absorb at a higher vibrational frequency. And similarly, the wave number or frequency that is inversely proportional to the reduced mass or the mass of the atoms, individual atoms. That means a bond made up of lighter atoms will vibrate at a faster frequency. Now let's see the application of Hooke's law to explain some trends in IR absorptions. For example, let us compare the IR frequencies of carbonyl group in a conjugated ketone and a non-conjugated ketone. For example, propiophenone and phenylacetone, they are structural isomers, you can see. The conjugated ketone absorbs at a lower frequency compared to the non-conjugated ketone. How can we explain that on the basis of Hooke's law? We can see that the strength of the bond decreases due to conjugation as the bond order or the double bond character decreases. That means it will be absorbing at a lower frequency. But here the double bond character is retained in this molecule phenylacetone. That means it will give a typical peak of the carbonyl group in the range 1715 centimeter inverse. That means in non-conjugated dienes, higher frequency of IR absorption is observed. Another trend is depending on the mass of the terminal atoms. Here we have three bonds as comparison: CH bond, CCl bond and CBr bond. Which will be absorbing at a higher frequency? Definitely the CH bond will be absorbing at a higher IR frequency, because as the atomic mass decreases, as per Hooke's law, the frequency or wave number is inversely proportional to mass of the atoms. That means the lighter atoms, bonds with the lighter atoms, they will be vibrating at a higher frequency and so will be absorbing in the high frequency region. So the order will be like CH, CCl and CBr. And similarly, the bond strength can be compared using C triple bond C, C double bond C and CC bond. Which will be having a higher frequency? The triple bond C triple bond C will be absorbing at a higher frequency. In the case of C bond or CO bond or CN bond, this kind of a trend is observed or a pattern is observed. That is because higher bond strength leads to higher frequency. Stronger bond will be vibrating at a higher frequency. So this is a problem based on Hooke's law. A strong absorption of IR radiation is observed for hydrogen chloride at 2991 centimeter inverse. So here we have given the fundamental vibrational frequency of HCl and we are asked to calculate the force constant of HCl. So how we do the problem? According to Hooke's law, nu is equal to 1 by 2 pi into square root of k by mu, and nu bar, the wave number, is equal to nu by c, that is 1 by 2 pi c into root k by mu. So first we can calculate mu as mu from the atomic masses of hydrogen and chlorine, as mu is equal to mh into mcl divided by mh plus mcl, where mH and mcl represents the atomic masses of hydrogen and chlorine. mH is 1.008 and that of atomic mass of chlorine is 35.453. So we'll be getting mu, the reduced mass of HCl, as 0.98 AMU. But we have to convert this AMU to kilogram by multiplying with the 1.67 into 10 raised to minus 27. And we have got mu value. Now you can substitute that in the equation. K is equal to, the force constant K is equal to nu bar square into 2 pi c whole square into mu. And nu bar is 2991 centimeter inverse, the vibrational frequency. Then 4 square pi square c square into 0.98 into 1.67 into 10 raised to minus 27. And we are getting the value in Newton per meter or kilogram per square centimeter. And the thing to remember is that you don't need to convert this vibrational frequency in centimeter inverse to meter inverse. Now we shall see the different types of vibrations. A molecule can have a stretching vibration and a bending vibration. And the stretching vibration can be of two types: symmetrical stretching and asymmetrical or anti-symmetrical stretching. As you can see here, in a symmetrical stretching, both the bonds will be stretching simultaneously. But in the case of asymmetric stretching, one bond will be stretching and the other one will be undergoing compression at the same time. So this is called the asymmetric or anti-symmetric stretching. And in bending vibrations, there are in-plane bending and out-plane bending vibrations. So in in-plane bending vibration, it will be in the XY plane itself. That is of two types. One is scissoring in-plane bending and rocking bending. So scissoring means it works like a scissor, as you can see here. both the bonds are coming closer like this. It works like a scissor. And rocking means both the bonds will be vibrating in the same direction. And among out of plane vibrations, we have wagging and twisting. As you can see here, wagging means it is like the movement of a tail, wagging of a tail, like both the bonds are coming out of the plane towards you simultaneously. Both the bonds are coming towards you simultaneously. But in twisting, what happens? One bond is coming towards you, at the same time the other bond is going in the opposite direction, like this. So bending is in opposite directions out of the plane. So wagging and twisting are the out of plane vibrations possible for a molecule. So this is a pictorial representation of different molecular vibrations on a two-dimensional plane, where we are using arrows to show in plane and out plane vibrations. So straight arrows for in plane and curved arrows for out of plane vibrations. Here, as you can see here, for symmetric stretching, two arrows represents that both the bonds are undergoing vibration simultaneously, stretching vibration simultaneously. And for asymmetric stretching, one bond is compressing and the other bond is stretching. And for scissoring and rocking, they are in plane. So here also you can use the straight arrows. So both the bonds are coming closer, as you can see here by the arrows, straight arrows. And here both the bonds are going in the same direction in rocking. And wagging and twisting, they are out of plane vibrations. So we have to use curved arrows like this to represent the vibrations. So this is bending towards you. Both the bonds are bending towards you, and here one bond is bending towards you and the other is bending backwards. That is called a twisting. So for a molecule having n number of atoms, its position in space is defined by three axes, right? X, Y and Z axis. So its total degrees of freedom will be 3n, which is a sum of its vibrational degrees of freedom, translational degrees of freedom and rotational degrees of freedom. So for a monoatomic molecule, the total degrees of freedom will be 3n. That means 3. That is 3 translational degrees of freedom is possible. 0 vibrational modes because there are no bonds here for a monoatomic molecule. But for a diatomic molecule like HCl, for example, for HCl, n is equal to 2. 2 atoms are present here. So 3n, that means 3 into 2, 6 number of degrees of freedom, total degrees of freedom is possible for a molecule, and out of that 6 number of freedom, 2 are rotational and 3 are translational. That means we have to subtract total 5 degrees of freedom in order to get the vibrational degrees of freedom. So that means the total vibrational degrees of freedom for a diatomic linear molecule will be 3n minus 5. So here for HCl it is 1. 3n minus 5 is 1. And for a triatomic linear molecule also, the same principle applies. It has a total of 5 other degrees of freedom. So in order to get the vibrational degrees of freedom, we have to subtract 5 from 3n. 3n is the total degrees of freedom. For carbon dioxide, a triatomic molecule, it will be 3 into 3, 9. 9 total, 9 degrees of freedom minus 2 translational and 3 rotation. 2 rotational and 3 translational degrees of freedom. So 3n minus 5 gives 4. So the molecule possesses 4 vibrational degrees of freedom. So this is a general rule for a linear molecule. For a linear molecule, the total vibrational degrees of freedom is governed by the 3n minus 5 rule. But for a triatomic non-linear molecule, for example water, what happens? It possesses 3 translational degrees of freedom and 3 rotational degrees of freedom as well. That means a total of 6 degrees of freedom has to be subtracted from the total 3n degrees of freedom. So that 3n minus 6 gives 3 for water molecule. So the vibrational degrees of freedom for a non-linear molecule is governed by 3n minus 6 rule. Now in our syllabus we have to study 2 specific IR spectrum and the analysis. One is carbon dioxide and the second one is water. Carbon dioxide is a linear molecule and it is having a zero net dipole moment, but still it has some motions in the IR region so that it can give rise to IR peaks. The total vibrational modes will be for a linear molecule. It is governed by 3n minus 5 rule. So 3 into 3 minus 5, that is 9 minus 5, 4 vibrations are possible for carbon dioxide molecule. So these 4 vibrations are as seen here. Symmetric stretching of the CO bonds like this, and this is anti-symmetric or asymmetric stretching, and 2 bending vibrations. One is out of plane and one is in plane bending vibration. So this is out of plane in XZ plane and this is in plane, that is XY plane. And both are degenerate. Both are degenerate means they are having same energy, so they will be give rise to degenerate bands in the similar region. And now consider the symmetric stretching of carbon dioxide molecule. And during this kind of vibration, there is no change in dipole moment observed. That means this particular vibration is not seen in IR spectrum. It is IR invisible. But the vibrational frequency is there. The symmetric stretching is at 1388 centimeter inverse and it is visible in Raman spectrum. Raman spectrum means it is complementary to IR spectrum. So that means symmetric stretching of carbon dioxide that is invisible in IR because it does not possess a permanent, a change in dipole moment, but it is seen in Raman spectroscopy. And the second one is anti-symmetric stretching vibration. Definitely that is seen in IR spectrum at 2349. As you can see here, it is a sharp downward peak at 2349 centimeter inverse. And the degenerate bends, they are seen in the fingerprint region at 667 centimeter inverse. Similarly, we can have an analysis of the IR spectrum of water. So water is a non-linear molecule and also it is possessing a permanent dipole. So all the vibrations in water molecule will be IR active. And the total number of vibrational modes possible is governed by 3n minus 6 rule because it's a non-linear molecule. 3 into 3, 9 minus 6, that means 3 vibrational modes are possible for water molecule as you see here. One is symmetric stretching, like this. Anti-symmetric stretching, where the OH bonds are one stretching and one compressing like that. And scissoring bending, in-plane bending vibration is seen in water molecule. Symmetric stretching and anti-symmetric stretching both fall in the same region 3756 and 3652. They are degenerate, giving a broad spectrum in this region around 3700 centimeter inverse. And the bending vibration that is seen here at 1595 centimeter inverse. Now let's see the applications of IR spectroscopy. As we have been discussing, it is a tool for the molecular structural analysis. That means to identify the functional groups, specific bonds by the corresponding frequencies present in IR spectrum. Then to determine the force constant by applying Hooke's law. Then to analyze unknown compounds, that means if you have an unknown sample, you can identify the functional groups present from the corresponding peaks in the spectrum. And a very important application is to distinguish intra and intermolecular hydrogen bonding. An example is orthonitrophenol and paranitrophenol. As you can see, due to the peculiar structure of orthonitrophenol, it can have an intramolecular hydrogen bonding or hydrogen bonding within the molecule itself. So paranitrophenol is having an intermolecular hydrogen bonding where a hydrogen bond is formed between two molecules. So how will you distinguish orthonitrophenol and paranitrophenol? Because both will be answering all the chemical tests due to their similar structure, but they can be easily distinguished in IR. because on dilution of the sample, the frequency of NO2 and OH in orthonitrophenol, that will not change because it is having an intramolecular hydrogen bonding. But in the case of paranitrophenol, if you are diluting the sample and again taking the spectrum, definitely the frequency of NO2 and OH will change as the molecules are falling apart. There will be a change in the bond strength here, and sometimes the bond, this hydrogen bond will break, so that there will be a frequency change of NO2 and OH in the spectrum. So that means for orthonitrophenol, the IR spectrum remains the same even on dilution, but for paranitrophenol, the frequencies of nitro group and OH group will change as the molecules are moving apart on dilution. And second one is in the quality control of drugs and perfumes. So in the case of drugs and perfumes, we are continuously in contact with such chemicals. So it is very important that these chemicals should be highly pure in nature. So the impurities can be found using this IR spectroscopy. And in forensic science, from a crime scene, we are getting very small quantities of samples like body fluids, saliva, etc. And we have to take utmost care in accurate analysis of these kind of samples from crime scene. For that, we are relying on IR spectroscopy. And the fourth one is in the study of polymers and complexes. You know that these are molecules having very complex structure. So in their structural analysis, IR is used as an analytical tool. Then drug analysis in blood sample. For that, we are applying IR instrument. So the drug molecules will be giving characteristic peaks in the IR spectrum. Then IR breath analysis of drunken drivers. You can see highway police with this IR breath analyzer. It is working on the principle of IR, where an alcohol molecule will be detected in the IR spectrum. And the most importantly, IR is used in space probes. This is Mars rover to find water molecules on Mars. So for space expeditions, we are using IR as a tool to identify molecules like water, carbon dioxide, etc. So IR spectroscopy is very significant because it is used or applied in various fields of research and analysis. So we shall conclude here. Thank you.